Hello, today I'm going to talk about our research titled Synthesis, Characterization, and Cytotoxic Evaluation of Niobium Pentoxide Nanoparticles and Quantum Dots for their safe use in biomedical applications. This work is the result of a collaboration between the Bioengineering and Nanomedicine Laboratory at the University of Guanajuato and SEMAV, joining forces to explore the potential of a little-studied material in the biomedical field, niobium pentoxide. Biomedicine has evolved rapidly, driving the use of nanomaterials as key tools in the diagnosis, treatment, and monitoring of diseases. This progress has encouraged the search for new biocompatible materials with unique properties to expand their medical applications. Niobium pentoxide is a metal oxide with semiconductor and photocatalytic properties and high thermodynamic stability, making it a promising candidate for advanced biomedical applications. This material presents various crystalline phases: monoclinic, pseudohexagonal, tetragonal, orthorhombic. The orthorhombic phase is the most studied due to its excellent photoelectrochemical performance and structural stability. Reducing the size of niobium pentoxide to the nanoscale significantly increases its specific surface area and reactivity, improving its photocatalytic capacity and its interaction with biological systems. When it reaches the size of quantum dots, quantum confinement effects occur, modifying its band gap and optical properties. This phenomenon opens up new possibilities for its use in bioimaging and optical sensors. However, this size reduction also could influence its biodistribution, cellular permeability, and toxicity profile, essential factors for ensuring its safety in medical applications. In the biomedical field, niobium pentoxide has been investigated for multiple applications including UV radiation protection, photocatalysis for the degradation of organic compounds, sensors, photodynamic therapy, and coating of orthopedic and dental implants. Recent research also evaluates its potential for controlled drug release, imaging, and tissue engineering. However, challenges remain regarding to its cytotoxicity and potential inflammatory effects. Based on the above, the following hypothesis is proposed. Niobium oxide nanoparticles, in their orthorhombic phase, are safe for biomedical applications, and by reducing their size to quantum dots, they maintain or improve their biocompatibility. And to test it, the following objective was established: to synthesize, characterize, and evaluate the biosafety of niobium pentoxide nanoparticles and quantum dots to explore their viability for biomedical applications. To confirm our hypothesis and meet our objectives, the following methodologies were carried out, which are based on the synthesis and characterization of nanomaterials and their in vitro evaluation. The synthesis of niobium oxide nanoparticles was carried out using the Pecchini method, which is based on the formation of a metal complex using a chelating agent, citric acid, and a polymerizing agent, ethylene glycol, which is then subjected to a thermal process to obtain the desired metal oxide. For the synthesis of niobium oxide quantum dots, a chemical etching treatment was used, which consists of using a strong acid to degrade the surface of the nanoparticles and thus reduce their size. Therefore, previously synthesized nanoparticles were used. In this study, the raw 264.7 cell line, murine macrophages, was used to determine whether exposure to niobium pentoxide NPs and QDs induces activation toward the pro-inflammatory N1 phenotype. To this end, nitric oxide production from nitrite accumulated in the medium was indirectly quantified using the modified Breese method. Furthermore, cytotoxicity was evaluated using the WSD1 assay, which is based on the reduction of soluble tetrazolium WSD1 by active mitochondrial enzymes, forming soluble red formazan salts. The amount of formazan generated is directly proportional to the number of metabolically active cells. Here we can see the average yield of nanomaterials obtained under the different synthesis conditions. In the case of niobium pentoxide nanoparticles, we obtained approximately 382 mg, while for quantum dots, the yield was lower, around 34 to 37 milligrams, depending on the acid treatment time. This difference is expected, since the process for obtaining quantum dots involves additional steps that reduce the final amount of material. In Section A, we observed the nanoparticles, which appear as fine white powders with a granular structure, and in Section B, the quantum dots, which have an even finer and more homogeneous texture, confirming the reduction in particle size. Scanning electron microscopy and transmission electron microscopy images, along with size distribution of niobium pentoxide nanoparticles and quantum dots obtained after different acid treatment times, 30 minutes and 1 hour. A progressive decrease in the average particle size is observed, from 26.3 plus minus 5.64 nanometers for nanoparticles to 18.37 plus minus 6.1 nanometers and 13.79 plus minus 4.47 nanometers for quantum dots treated for 30 minutes and 1 hour, respectively. Furthermore, it is observed that the morphology with the most pedromen in NPs and QDs is quasi-spherical. UV vis absorption spectroscopy of niobium pentoxide nanoparticles and quantum dots showed an absorption maximum at 262 nanometers for nanoparticles, with a broad absorption curve, and for quantum dots, obtained after 30 minutes and 1 hour of chemical etching, it showed an absorption maximum at 260 nanometers, with narrower and more defined spectral profiles. This shift of the absorption maximum towards shorter wavelengths, known as blue shift, suggests a decrease in the effective particle size, characteristic of the quantum confinement effect. Furthermore, the torque plot helped us determine the bandgap energy of niobium pentoxide nanoparticles and quantum dots. A value of 3.33 electron volts was obtained for nanoparticles, 3.55 electron volts for 30-minute quantum dots, and 3.48 electron volts for 1-hour quantum dots. These values demonstrate a widening of the forbidden band, which indicates the existence of quantum confinement. To confirm the crystalline phase of the nanoparticles and quantum dots of niobium pentoxide, the X-ray diffraction technique was performed and the data obtained were compared with the crystallographic charts of the International Center for Diffraction Data, ICDD, and it was observed that chart number 30-0873, which corresponds to the orthorhombic phase of niobium pentoxide, was the most similar. In turn, the diffractograms of the quantum dots obtained after 30 and 60 minutes of chemical etching did not show a phase change with respect to the original material. Based on the results of the quantification of nitric oxide released by raw 264.7 macrophages after 36 hours of exposure to different concentrations of the nanomaterials, a statistical analysis was performed using the nonparametric Kruskal-Wallis test. This revealed statistically significant differences between the negative control and the lipopolysaccharide treated group, as well as between the lipopolysaccharide group and all the evaluated concentrations of nanoparticles and quantum dots. However, no significant differences were detected between the different concentrations of the nanomaterials compared to the negative control, suggesting that none of the treatments evaluated induced a pro-inflammatory response. On the other hand, the results of the WST1 assay showed no significant differences between the conditions evaluated with the different materials, compared to the negative control. These results suggest that, under the experimental conditions used, none of the nanomaterials evaluated significantly affected cellular metabolism, which reinforces their potential biocompatibility. The results obtained confirm that niobium pentoxide nanoparticles in the orthorhombic phase present a defined structure and controlled size, as well as good in vitro biocompatibility. Obtaining quantum dots from these nanoparticles by chemical etching allowed their size to be reduced, without compromising their stability or inducing cytotoxic or pro-inflammatory effects. These results position niobium pentoxide as a promising material for future biomedical applications, although additional studies will be necessary to validate its in vivo behavior and specific functionalization.